Hi, my name is Philip and I am a member of the ExplainMe team. In these parts, I will present the modeling approach used in our project. The goal is to monitor acoustic features extracted from speech and use them to detect possible changes in the patient's mental state. In particular, we focus on distinguishing euthemic calls from depressive or subdepressive ones while keeping the model transparent and interpretable. The main modeling question is, after patient-specific standardization, is the call unusually far from the euthemic reference state? This is crucial as speech differs naturally across people. Age, sex, language, personality, and recording conditions can all affect acoustic features. Therefore, a global notion of normal speech may be misleading and standardization is needed. So instead, we use an anomaly detection perspective where a call is first expressed relative to the patient's own euthemic baseline and only then compared on a common standardized scale across patients. The illustrative example shows why this matters. The same new call may be highly unusual for one patient but completely normal for another. The original data are frame-level acoustic features extracted from speech recordings. In total, we start with over 270,000 frames and 292 acoustic features. Since the clinical label is assigned at the call level, we aggregate the frame-level features into call-level summaries. For each selected acoustic feature, we compute summaries such as the mean, standard deviation, skewness, and maximum. Then, we perform expert feature selection. The aim is not only dimensionality reduction but also interpretability. We focus on features related to pitch, energy, loudness, and voice quality. This gives us a preprocessed modeling matrix with 346 calls, 20 patients, and 39 interpretable call-level features, as one feature exhibits only a single value and therefore is dropped. Next, we perform the final preprocessing step. First, we remove states such as hypomania, mania, and mixed state because there are too few calls in these categories to model them reliably. Then, we merge depression and subdepression into one non-euthemic class, so the final task becomes binary, euthemic versus depressive or subdepressive. Finally, we keep only patients for whom the anomaly detection setup is meaningful. In particular, a patient must have at least 2 euthemic calls so that we can estimate their baseline, and at least one non-euthemic call so that the model can be evaluated. After this filtering, the final dataset contains 251 calls from 20 patients. Now I will describe the model itself. Let xi be the acoustic feature vector for call I, and let p of I denote the patient who made that call. The class label is yi, where 0 denotes euthymia and 1 denotes the depressive or subdepressive state. For each patient, we define the set of their euthemic calls. Using only these calls, we estimate the patient-specific euthemic mean vector and standard deviation vector. Then, each call is standardized relative to the corresponding patient's euthemic baseline. That is, we subtract the patient's own euthemic mean and divide by the patient's own euthemic variability. The small parameter epsilon is used as the numerical floor for the standard deviation so that we avoid division by values that are 0 or extremely close to 0. The result is a standardized vector which expresses the call as deviations from the patient's own stable state. After standardization, the classifier is intentionally simple. For each call, we compute the abnormality score. So the score is the sum of squared standardized deviations over all selected acoustic features. Large values of S indicates that the call differs strongly from the euthemic baseline. The final prediction is obtained by thresholding the score. A call is classified as non-euthemic if S is greater than or equal to the threshold Q tau. The threshold Q tau is estimated from the abnormality scores of euthemic calls in the training data. More precisely, it is the empirical tau quantile of the euthemic training scores. So, the parameter tau controls how conservative the anomaly detection is. Higher values of tau produce a higher threshold, and lower values make the model more sensitive to deviations. The threshold is tuned using nested patient-wise cross-validation. In the outer loop, we leave one patient out. This means that all calls from one patient are held out as the test set, and the model is trained using the remaining patients. Inside the training set, we perform patient group cross-validation to choose the quantile level tau. The candidate values range from 0.65 to 0.99. The selection criterion is the average of F2 score and balanced accuracy. Balanced accuracy protects performance on both classes, while F2 gives additional weight to the recall of non-euthemic calls. This is important due to the fact that, in the monitoring context, missing a depressive or subdepressive state might be more problematic than producing an occasional false alarm. After selecting tau, the threshold is refitted on all outer training patients and then evaluated on the held-out patient. This avoids patient leakage during threshold tuning. The table shows the results of the outer cross-validation across held-out patients. The mean balanced accuracy is about 0.73, and the mean combined criterion, defined as the average of balanced accuracy and F2, is about 0.69. The results suggest that patient-specific acoustic deviations contain useful signal for detecting depressive or subdepressive states. At the same time, the variability across patients is high. This is visible in the standard deviations and interquartile ranges. So these results should be interpreted as promising but still preliminary, especially given the small cohorts and the heterogeneity of depressive speech patterns. The main contribution of this model is that it provides a white box anomaly score for speech-based monitoring. It uses patient-specific normalization, so it reduces between-person heterogeneity and focuses on within-patient change. The validation is also patient-wise, which gives a more realistic estimate of generalization to unseen individuals. Another important advantage is interpretability. Since the score is a sum of feature-level contributions, each prediction can be explained by identifying which acoustic features contributed most strongly to the deviation. The key limitation is that the model requires an euthemic baseline for each new patient. Prediction is only possible after observing enough euthemic calls to estimate that patient's reference distribution. Thank you and have a great day.